In part A, we find the general solution of this differential equation. And so this differential equation can be solved by separating the variables first and then integrating it. So first, I'm going to divide both sides by this expression 650 over n. So I write dn divided by dt, and this is divided by 650 minus n, and this equals k times of 650 minus n divided by 650 minus n. So this simplifies to these two factors gets cancelled, and here on this left side I have 1 over 650 minus n times dn over dt, and this equals k. Now I multiply both sides by dt, and so I get I'm sorry, this is dn over dt. I can write this as dn over 650 minus n, and this equals k times of dt. So we have separated the variables, that is all n variables onto the left side and the t variables onto the right side. Now we integrate so that we can determine the general solution. Integration of 1 over 650 minus n, and this equals negative of natural logarithm of 650 minus n. This is absolute value, and this equals if we integrate k dt, k is a constant, and then integration of dt is just t. We also put the integration constant, which is c1. Now let's divide both sides by negative. Therefore, we get natural logarithm of 650 minus n within absolute value, and this equals negative kt negative c1. Now we raise both sides to the exponent e. So this side we have to raise to the e, and this side also we raise e to this exponent. So e and natural logarithm are inverse to each other, they cancel out. So on the left side we have 650 minus n, and this equals on the right side we have e raised to the power of negative kt negative c1. Let's simplify this further and solve for n. I'm going to split this as two exponents, that is e raised to the power of negative kt times e raised to the power of negative c1, and I replace e raised to the power of negative c1 as another constant c, because basically this is going to be a constant, so we can just replace this as a constant. So therefore this equals capital C e raised to the power of negative kt, and on the left side we have 650 minus n, and therefore we add n to both sides, we get 650 equals n plus c times of e raised to the power of kt. Now we subtract c times of e power minus kt on both sides and solve for n. So therefore we get n equals 650 minus c times of e raised to the power of negative kt. And so this is the general solution of the differential equation. In fact, we can replace this n as a function of t, that is n of t. So we have the solution n of t equals 650 minus c e raised to the power of negative kt. Let's do part B. Here we find the particular solution of the differential equation using this initial condition, that is when t equal to 0 the population is 300, and when t equals 2 the population is 500. So first let's plug in the value of t equal to 0 and n of t equal to 300 into the general solution. Therefore when t equal to 0 it is n of 0, and this equals 650 minus c e raised to the power of negative k times of 0. N of 0 equals 300. So I put 300 here, and this equals 650 minus c times of this is e power 0 is 1. So it is negative c. So 300 minus 650 is negative 350. and this equals negative c. So this gives c equals 350. We can plug this value into the general solution. So therefore, we can rewrite n of t equals 650 minus c times, that is 350 e raised to the power of negative kt. Now let's use the second initial condition, that is when t equal to 2, n of t equal to 500. So let's plug in t equal to 2 and n of t, which is n of 2, and this basically equals 500. Therefore, this is n of 2 equals 650 minus 350 times e raised to the power of negative k times of 2. N of 2 equals 500. So replace n of 2 by 500 equals 650 minus 350 times e raised to the power of negative 2k. Let's add this expression to both sides and subtract 500 to both sides. So therefore, we can write down as 350 times e raised to the power of negative 2k, and this equals 650 minus 500, and so this equals 150. We have 350 times e raised to the power of negative 2k. Now we divide both sides by 350, so we get e raised to the power of negative 2k, and this equals 150 divided by 350, and this simplifies. We can cancel the trailing zeros. This is 3 fifth and 7 fifth, so it basically reduces to the fraction 3 over 7. So we have the equation e raised to the power of negative 2k equals 3 sevenths. Now to solve for k, we have to take a natural logarithm on both sides. So we apply natural logarithm. Therefore, we get natural logarithm of e raised to the power of negative 2k, and this equals natural logarithm of 3 sevenths. And using the property of natural logarithm, we can bring this power of e, which is negative 2k, and then times natural logarithm of e. This equals natural logarithm of 3 sevenths. And we know that natural logarithm of e equals 1. So this simply reduces to 1. And on the left side, we will have negative 2k, and this equals natural logarithm of 3 sevenths. And solving for k, we divide both sides by negative 2. So we get k equals natural logarithm of 3 sevenths divided by negative 2. And plugging this expression into the calculator, we get approximately k is approximately 0.4236. This is rounded to 4 decimal places. So we determine the value of k, and so we can now write the particular solution of this differential equation. We plug it into this equation after we have determined the value of c. So we can write n of t. This equals 650 minus 350 times e raised to the power of negative kt. So replace k, that is negative of 0.4236. This is 6t. Then multiply with t. So this is the particular solution of the differential equation. In part C, we determine the population when t equal to 3. So we have to plug in t equal to 3 into the particular solution that we found in part B. So therefore, it becomes n of 3, and this equals 650 minus 350 times e raised to the power of negative 0.4236 times 3. And so when we plug this expression into the calculator and approximate to whole number, we approximately get 552, and this is coyotes. So therefore, when t equal to 3, the population is 552 coyotes.